Welcome back to Area DMG. I'm your host, Will Wesley, the Mile High Mouth, and the video you are about to see is the Climate Change Hard Data Panel from MileHighCon 2016. Now, I was a little hesitant to release this because there are issues with the audio, issues with the video. I actually recommend that you check this out with headphones on, and it ends abruptly. What happened was, at MileHighCon, there were a bunch of scientists and engineers who got together and said, hey, let's do a panel about climate change and present just data. And there's a little bit of opinion in it too. I mean, what you'll find about climate change is that if anyone ever tells you it's settled science, they are trying to sell you their latest DVD box set. And that's wrong. They're trying to profit off of it. If anyone ever tells you there's a consensus, no, that's not how science works at all. Let me tell you how science works. And there are people who will disagree with this because this is my theory on how science works. A scientist is a person who wants to know more about what is around them. They want to know more about their world. And they go into it by finding more things. You want to see if what you've been told is real. You have to challenge everything. You have to challenge with fervor everything. If you look at something and go, well, it's settled, that takes all the joy and fun out of it. No. We need to know more about that. Is there water on Pluto? What is down there in the deepest parts of the ocean? Is what we know about plants correct? We have found so many different things. How do we affect the climate channel, the climate? How do we not affect the climate? Is our existence an infinitesimal drop in a vast ocean? Actually, I think the answer to that last one is yes. And no, I don't think that we have a complete and lasting effect on the entirety of the environment. A lot of the environmental science, or rather the people who want to tell you about carbon credits or whatnot, the people who want you to send them their money, are banking on the idea that you will look and say, well, if a butterfly flaps its wings in Tokyo, there's going to be an earthquake in San Francisco. No. And also yes, but not in the way that you think. I implore you to check out this data. It's interesting. It's not all complete, and not all of it's completely clear, but it is interesting to watch. If you can follow this, you're going to love it. If you don't, or can't follow it, put it on the background. Listen to these people ramble a bit. It's going to be interesting. Generally, you're going to find an interesting conversation is being had in this panel. And unfortunately, they didn't have enough time to do it because each of these scientists brought like 60 panels or slides to this panel. And there's no way they were ever going to get through that. And they argue with each other a bit too, which is fun. It's good stuff. I liked it. I really enjoyed this panel. Unfortunately, I felt that the taping and recording that we had of it wasn't the best quality. But I'm not going to deprive you of that, even if I don't feel that it's the best quality and that it ends abruptly. So, check out this footage. We're going to go right into it and enjoy, I suppose.
Okay, let's go ahead and start. You can see the title slide, and it lists all of our panelists. So why don't I let the panelists introduce themselves in alphabetical order here. So Ray, you start.
Hi, I'm Ray Bueland. I'm a retired geophysicist, so I'm not a climate scientist, but I'm...
Speak up a little bit, please.
No!
Okay, I tried. Yeah, I tried.
I'm a retired geophysicist with an interest in climate, so...
Greetings everyone, thank you for coming, especially bearing with us with our technical difficulties. I'm Dr. Leslie Smith. I work at CU at the Cooperative Institute for Research in Environmental Science, and for some reason there's a huge long list of my areas of expertise on the slide. I don't know why. I'm also a science fiction author, and my bio in the handbook talks about my latest book, The Quantum Cop. Hopefully we'll have a fun panel tonight.
I'm Robert Williscroft. Doesn't say anything about my background there, but I'm a retired submarine officer, deep sea diver. I've got a PhD in engineering, not in climate scientist, but I did spend 1 year at the Geographic South Pole in charge of NSF atmospheric science research.
My name's Courtney Willis, and I've been a teacher all my life until this fall when classes started and I didn't. So I'm now retired myself. So we've got a couple of old guys who have no idea what we're talking about.
Okay, yeah, I'm Steve DeLima. I'm more of an engineer than a climate scientist, but do work on instrumentation for measuring climate. Worked on the instrument for the Mars Climate Sounder. And I'm also an expert reviewer for the IPPCC, which probably is not as hard to be as if you really wanted to. It certainly doesn't pay. So anyway, when we get started, the plan for this panel is to really look at hard data on actual climate observations. We get into so many arguments about what projections are and what models say and all that kind of stuff. But I think there's a lot of information in the news, on all sides of the issue that's pretty absolutely wrong. I'd really like to see good information get out there. So we're going to hopefully show some good information and have a lively discussion about it. And some of it contradicts the other information, so I'm sure we'll be more on top. So to get started, there's been a lot of discussion this year and even some last year whether 2015 and now 2016 are going to have the highest recorded average temperature ever. And if you look at the satellite data, which we're showing on the screen there, it shows that there's a very close race between where we are here in 2016 and what it was, if I can use in 1998. Both of these years were the El Nino years, which I think Leslie should be able to tell us something about that. But those are years when especially the satellite temperature measurements show very high temperatures. It's also interesting, I think, that the first year of the El Nino then, in 97, was the year of NARCON, if anyone remembers that.
Yes.
And also last year, just before Mile High Con, we had a big snowstorm. So, I don't know, is that a real El Nino effect here?
That would be over a whole hour discussion in itself.
Okay. So I don't know, does anyone have some comments they want to make on this? Is this surprising?
So one of the official questions is, was 2016 one of the warmest ever recorded? That's one of our official questions, and what do we say here?
Well, at least this particular data, I think, says that unless the temperature drops rapidly in the last couple of months of the year, yes, it probably will be, but just barely. It's not obvious that it is a big change. Now, I guess we can go on to the next slide, which shows not satellite data, but surface temperature data. Second slide. I'm looking at the right one, otherwise.
So they were talking that we might break a record today. I didn't hear it. Did we break it? Hottest temperature for the state? Anybody here?
It was very nice outside.
It was nice.
In any case, so we're seeing the surface station data. This is from the NASA Goddard Institute for Space Studies, which is one of several temperature indices. And if you look at this one, it's not even close. It looks like that it's definitely, according to this particular data, that it is a lot warmer than what it has been. Although it has already, as you can see, returned back to the levels of its very high temperatures. Again, probably a El Nino effect rather than something permanent.
Yeah, but this also shows yearly variation through there too. So, you know, the northern hemisphere has just finished summer. So, since this is surface, it should probably be the warmer, and then be going back down now.
All right. So go on to the next slide, please. And so one thing we mentioned is there are a number of different groups that look at temperatures. And I think this slide is one that Courtney put together. Although I think this is probably my title on it. That shows that you get pretty much the same information from all these groups. Just if you do a little bit of smoothing, you see there. But it's also that they're all working with kind of the same data from the various stations around the world. So maybe it's not that surprising if they really do pretty well. It's your slide. You might want to talk a little about Berkeley Earth. I know you have a lot.
Right. I had collected a few slides, and then we had a power outage and I lost everything. So what I sent in were just some of the slides from Berkeley Earth. Berkeley Earth started, I think, in 2010 to try and look at this phenomena, global warming and stuff. And they were particularly interested in looking at raw data, not other data and stuff. And so this shows various data from NASA, NOAA, and from Berkeley Earth there in black. And the gray band there, since everything's statistical, that gives you the 95% probability. And you can see it's roughly the same width as we go along there, but and it pretty much covers most everything.
So I have a question. What does that mean? What does that vertical axis tell you?
What does the vertical axis mean? So this is what's, one, it's a global average. And then the anomaly means that's how it's different from what some baseline temperature was. I think it says down there in the fine print that this is relative to what the January 51 to December 1980 baseline was. So we just took the average temperature over that 30-year period. And for each month or even each day, depending on how it's done, I guess, and see whether it's warmer or colder than that average by this many degrees. So in general, they're saying that yes, this graph doesn't go quite as, this ends in 2014, so you don't see the peak that we saw, but it says that we're about 5 or 6/10 of a degree above what the average was over that 1950 and 1980.
Let me add one thing here. If you notice, you have an increase, a very visual, clear increase along here, and from here moving forward, it's a little bit more difficult looking at it, at least visually, to see whether we still have an increase in temperature at this point. It just as an observation. I'll talk a little bit about that later.
So that's global temperature. This is land and ocean climate. So it's talking land temperature and ocean temperature.
Yes, but it's taking the
Surface temperature.
yes, the surface temperature, from measurements at weather stations, all over the world, and then also measurements of the ocean. The measurements in the ocean have improved drastically over the years. They used to just mostly be from ships. Early days, it was just sailors throwing a bucket over the end of the ship and filling up some water and measuring the temperature. Then more recently, they used the temperature of the cooling water inlet to the engines. And now we have buoys going floating all over the world to measure it. So it's much more accurate than it used to be. Yeah.
What is HAD CRU and what is Calvin Whale?
I don't know, Leslie, do you know all the acronyms? I can guess. I mean, the HADSI area is Hadley Climate Research Unit in Britain, right?
Yes.
It's at the University of East Anglia, I believe, in Britain. NASAGIS is the NASA Goddard Institute for Space Studies. NOAA is National Oceanographic.
There's the Oceanic Atmosphere.
And Cotton and Way are a couple of people that have published their own index that purport to make some corrections to the others. It's not a whole lot different. And then Courtney was telling you about the Berkeley group. Thank you. Yep. Yeah, please do ask questions as we go along. We don't need to wait till the end. Unless you want to get into a controversial argument, then I wait till the end. So ask questions as we go along. All right. So if we keep going, the previous data only went back to 1980, but there were measurements made back in the 1800s, and so there is data going back much further. And one of the things you'll notice is that while there's lots of variation and a lot of uncertainty back there in the early times, there was a very large increase in temperature from about 1910 to 1935, leveled off, and then more recently taken off fairly rapidly. And at least a lot of people pointed out that this increase is kind of similar in magnitude to that one. And at least for a lot of the reasons that people claim the temperature is increasing weren't happening back then. So that's something to be explained.
I'm sure I agree.
Well, okay, come on, talk.
What are you saying wasn't happening?
So around 1900 actually is when we first started the Industrial Revolution. And it was all that coal burning, and that's usually when people say that.
Well, Industrial Revolution started earlier, but I'm thinking, when did the use of petroleum take off?
It's around that time, 1900-ish.
I know we're getting ahead of ourselves a little bit.
Sorry.
Good. Well, no, that's good.
Just one thing I wanted to mention here. This is from the Berkeley Earth 2, and the reason I like the little gray there, you can see lots of uncertainty in here in the 1850s to 1900 because there weren't that many weather stations and stuff, so they have lots of uncertainty. And as you go up here, the uncertainty gets much, much smaller. You don't see much of that uncertainty in there because we're taking data from a lot more places.
Let's just go to the next slide, I guess. The next slide is similar data, just looking at oceans. It doesn't look really a whole lot different. Right? I mean, the numbers are different and probably not nearly as many measurements, especially long ago, but it's still the same kind of thing. And I guess I'm still going to point out that there's still the big increase from 1900 to 1945 and a similar increase later. But we'll talk about that as we go. So we can keep going back further in time. It gets much, much more uncertain. So now we're looking at millions of years, right? So this is the present over here on the right, and this is millions of years ago. And the data is based on isotope ratios of oxygen. And, I don't know, again, Leslie, maybe you know a lot more about exactly how that data is taken.
It's quite complicated.
So anyway, so this is, it's what's called a proxy for the temperature. That if you look at the difference in isotopes of oxygen 18 and 16, the sea creatures that were absorbing oxygen at that time, I guess, have a different ratio of isotopes. Then you can infer the temperature because they do it differently depending on the temperature. It also has something to do with rainfall too, doesn't it? But anyway, at least if you believe it, there's a calibration in terms of temperature over here, in terms of degrees C, and you can see all the ice ages that we've had up and down. So you go back 3 million years ago or so, no ice ages. Question?
So what does this chart actually mean, though? With the, I guess in a simpler term, of
Well,
I just don't understand what this chart means. I guess.
okay, so this is telling us what the temperature of the planet was millions of years ago.
Okay.
And there's a lot of things you can see. I mean, one, it was warmer back then than it is now, right? This 0 is supposed to be present day temperature. So, 4 million years ago, 5 million years ago, it was warmer than it is now. Yeah, at least according to the data. I mean, it could be that this is not extremely accurate.
Might point out that 5 million years ago is about when modern man started to emerge, and modern civilization is in about the last quarter inch there.
Yeah, it did survive the ice ages, although it's not necessarily easy. Yes, questions?
Back there 5 million years ago, was there more oxygen in there?
There was a little bit more, not, but it's been declining very, very slowly over millions of years. So a few percent.
Not just the oxygen, the air pressure was higher then too, wasn't it?
I don't know about that.
What was
There's
higher?
some things that indicate that.
Air pressure.
That's a hard thing to measure.
Yeah, it's probably hard to measure. It's a lot easier to measure the ratios of things than the absolute values of things.
To answer maybe what people are getting at there, 5 million years ago wasn't that long ago. You go back to when there were 20 dragonflies with a 24-inch wingspan. Those were only possible because the partial pressure of oxygen was a lot more than it is now. Insects do not have lungs. The only way you could have a flying insect that large, it's conjectured anyway, is if there was a lot more oxygen so their inefficient breathing mechanism could work at that size.
Yeah,
But that's hundreds of millions of years ago, much longer.
Yeah, that's an interesting proxy for what the oxygen is.
But I had a question, so the 41 kiloyear cycle, 100 kiloyear cycle, is that referring to the average length of a glacier advance and retreat?
It's the time between the warm intervals. So
So,
there's a cycle where there's long glacial intervals, and then there's a short warm interval to warm interval. That time period has changed over time, and it's related to astronomical properties, which is why it's so regular.
so glaciers used to advance and retreat on a 41,000 year cycle?
This is the whole glaciation. It's not just a glacier. It's like the whole Earth is getting
Whole Earth,
colder.
yes.
Yeah.
But then that cycle got longer a million years ago.
Yes. Technically, the entire 3 million year period there is an ice age. And what we're looking at is glacial intervals that right now are running around 100,000 years. The current warm period's been about the last 12,000 years.
Okay. Guess we can go on. So this particular slide is kind of coming back to the present. I saw this published recently, very recently, that it was kind of published in the context of why aren't people worried about climate change? And it's interesting if you look at these graphs. The first one is what the I could read it. I hope. It's the mean maximum temperature in January, and that has been increasing. And the second one is the maximum temperature in July. It's been almost constant. Similar things for relative humidity. It's been relatively constant with a lot of variation. And annual precipitation has been relatively constant. And I think the bottom set of here is kind of people's perception of what's good weather. Now, exactly how they determine that, of course, is probably rather subjective. But at least the climate change that there's been in the United States is something that at least most people would say is improving the weather. I don't know what comments the other panelists would have about
Now,
that.
let me make a comment about these charts here, and this is just those of you who aren't experienced with it. You notice this, the spots, the data points are all over the place, and there's a statistical technique for creating these lines, but you can pretty much make these lines go just about where you want them to. It isn't, don't take that as gospel one way or the other.
Yeah, well, although I think you can still kind of say that, yes, the January temperature has increased, right? There's a lot of low temperatures back in the 70s and a lot of high temperatures more recently. Now, saying that, yeah, this is any kind of an exact thing is, of course, very questionable. But anyway, I just thought
we have the panel now.
Yeah. So anyway, I just thought it was interesting that most people's perception, if they just look at what they feel, is, yeah, the weather's getting better. Right? We like it to be warmer in January.
It depends on where you live. It looks better here. It doesn't look better everywhere. I think that's part of the problem is that if you live in a place that's already very hot and it gets a little hotter, that's not good. If you live in a place that's moderate temperature, you might like it. If you live in the Arctic and the ice you live on starts to melt, things get ugly.
You still might enjoy the temperatures.
We might, but they're starting to have to move people inland because of storm surges and so forth, and the ice melting near the coasts. And you have to be careful when you talk about global averages.
When you look at the Arctic, it can be very critical whether the ice is still there during the roughest wave action. And if it isn't, your village could disappear, and that has happened to a few villages now.
Yeah, from the wave action. Okay, well, this next slide is Ray's slide, so go ahead and explain it.
Okay, thank you.
He makes me do that.
Wow, I've never been able to make
It's humiliating.
Laser poison. Okay. Yeah. I try to never use those, but okay, thanks. Okay, so this is from basically the Department of Agriculture in the U.S. They print these maps of agricultural zones which tell you what the maximum temperature during the growing season is, or minimum temperature. And what they're looking at is what kind of crops will grow in certain areas. And so those bands that you're seeing are, what they've done is they've done it at some point in the past and at the present, and those are the differences. And what's basically happening is that our perception of weather and seasons and so forth is very localized. Those climate trends are really, really long, and over decades what's happening is those zones are slowly moving north. And so you can now not plant certain crops farther south than you used to be able to because it's too hot. You can plant things farther north because it's now warm enough to do it. And we're seeing the same kind of thing here. It's getting to the point where the weather is warm enough here that it's hard for pine trees to survive because of the various pests that they have are doing very, very well in the warmer climate. I mean, if I was a pine tree and got warmer, I'd be happy, but being eaten by pine beetles is not so good. So that's basically what this is telling you, is that over a very long trend, we're seeing things move northward.
So basically, the bottom is where it was 10 years ago, and the top of each line is where it is now?
Yeah, and the colored things are just showing the differences. Yeah, it's showing the differences between that it's all black where they're the same as they were before. And so if you didn't have the explanation that they're moving north, you couldn't tell. You could tell they were moving, but not what direction.
Yeah, I had not seen that particular data before. It was pretty interesting. So, we've seen lots of data that says that things are getting warmer. Do we have a reason why it's getting warmer? And this is where it starts getting more controversial, but still, I don't know, depending on which of the panelists you talk to, probably how controversial it is. So why is the climate changing now? Certainly greenhouse gases, which is something that at least we can measure accurately. Finally came to something we can measure, right? And say that this is accurate, is a prime suspect. And this is the, I guess, famous Keeling curve. Keeling was the guy who back in the late 50s decided it might be important to measure carbon dioxide. And I think it's very good that he did, and he set it up to do that. And his early measurements were down there, just about 310 parts per million. So that's about 0.03%. And you see that wiggle in the line, which I think is very interesting because that is definitely yearly. I don't know, Ray, you had a very good explanation for it at your talk earlier.
Yes.
It's obviously partly plants absorbing carbon dioxide as they grow, and then when they decay, they give some off. But you had even more details to that. So.
Yeah, well, I mean, basically that's right. As plants are growing, they're bringing in carbon dioxide and emitting oxygen, but they're making starches to get them through the winter. And so in the wintertime, they do the reverse. So there's actually a cycle, right? They're bringing in oxygen, breaking down those starches, burning them for energy, and releasing carbon dioxide. The reason you see that pattern is that there's a lot more land in the northern hemisphere. So it's actually dominated by the northern hemisphere pattern. If it was equal in the northern and southern, it would smooth it out, right? So that's what you're seeing is the northern hemisphere agricultural cycle, basically, the plant growing cycle.
So anyway, one piece of data that we I think is pretty reliable. Of course, you could say, well, where is this carbon dioxide coming from? It's definitely increasing, and at least increasing at a much more rapid rate than it was in the 1960s. So it wasn't increasing so fast there, and you could imagine going backwards and say, well, okay, it probably wasn't too far below 300 parts per million. At least other data says that, 280 parts per million was the pre-industrial average. So it has taken off quite a bit, although I would say over the last 20 years, maybe that's fairly linear. At least this is not exponential, which I've heard some people claim.
I think it's pretty hard to say based on
that
graph. you
don't have enough data, yes, to really. But if it really was exponential, it would be.
Depends on where you start.
That's right. For a basis of comparison, though, if you look at CO2 from ice cores over the last few cycles of, not ice ages. What is the right word?
Glacial periods and warm periods.
Right.
Interglacials.
Okay, you look over the past half a dozen glacial periods and warm periods, CO2 would keep sawtoothing between 180 parts per million at the low, 280 parts per million at the high, and we're now up to 400 parts per million. So we now are in a part of the parameter space the Earth hasn't been in for a very long time.
Yeah, we have a slide coming up of how long ago. So
sorry?
We have a slide coming up of how long ago.
Okay.
Yeah. Although it should go back to where it was really high. They aren't very accurate.
Certainly true. So anyway, this is data that we have. We go on to the next slide. So where is the carbon coming from? And so there certainly is information about how much coal has been burned, how much oil has been burned, how much natural gas, and how much cement is made, which making cement also releases CO2. And so these numbers are probably reasonably accurate. I would say they're probably very accurate for developed countries, maybe not so accurate for other parts of the world, but still, overall, probably pretty good. And then this is from the IPCC, just trying to figure out, well, where is that carbon going? This is what's been emitted. So this gray is the same as that. It's the same data. And they're saying, well, okay, how much has land use change contributed to emitting carbon and cutting down trees and things like that. So that's added that. And then there's where is the carbon going? Besides from, we had carbon come in, cutting down trees and burning fossil fuels, it has to be going somewhere. Some of it's going into the atmosphere, and that is the light blue in here. But that's not anywhere near all of it, right? It's much less than half. So the rest of it's going someplace else. There's models that say how much is going into the ocean. That's what this is. And then basically green is everything else. Theory it must be going into land.
Is that a fire alarm? Never.
So Steve mentioned the IPCC. That I actually, my acronym was just wrong. But it's the Intergovernmental Panel on Climate Change, and it's a United Nations program. And they have tons of info about all this, and it's free. Anybody can read any of that stuff. So IPCC. I recommend it if you're interested in this kind of stuff.
Anybody can look at it. It's heavy going in places.
I'm just worried a little bit about the time. Yeah, I don't know how many more slides you have.
Oh,
but,
100.
Yeah, but one question I want to throw out. I think that most people with some neutrality would say, yeah, there's definitely climate change, definitely it's human caused by probably fossil fuels, carbon-based fuels. But one of the issues that seems to be the most contentious from what I've heard is the modeling of long-term effects. There seems to be a huge battle about that. I'd like comments from you folks about that.
Yeah, we could probably try to get to that sometime before we're done, although modeling isn't really part of this panel, because that's where you get into lots of arguments. But we'll try to touch on it before we're done. Let's talk about this next slide, because this is one that at least I saw published recently, and had not really seen this, at least this clearly before. I thought it was very interesting. Now, everyone is saying what we're doing to the planet is horrible for the planet. It could be bad for people, I don't know, but the planet likes carbon dioxide, right? I mean, this is what this is what the, you need to move it just a little further, you can't see the code there. This is the change in leaf area from 1982 to 2015 from satellite data. And it just shows that, at least in many places, there are 25, 30, 50% changes in plant density. I don't know how you want to exactly describe that. That the Earth is getting much greener. I mean, there's a very few places where there's less plant life, but some of that's probably statistical. And you were talking about the variations in carbon dioxide over the glaciations. That if CO2 gets lower than a couple hundred parts per million, it's very difficult for plants to grow. And it's very easy to grow for them to grow as it gets higher. So there are some probably very good things from releasing fossil fuels, in my opinion.
Well, I think you have to be careful. As you go back through the fossil record, there are periods where it was very, very much warmer than it is now. Maybe a lot more CO2, very different from how it is now. And it was always good for some group of living things. And I don't think that's the point here. I think what we're trying to decide is if it's good for us personally.
That's certainly true, at least for most people. Although I've heard a number of people saying, no, humans are not important, it's the planet that's important.
I think that's a very noble ambition. Not for me.
Yeah.
So I'm a sci-fi author. I released my first book last year. I'm working on the sequel now. And a lot of the backstory I have in my book has to do, there's creative license to it, but a lot of it was short-term, very drastic climate change. It takes place in 2150. So my question for you guys would be, for each of you, what do each of you think is the best thing that we could do? Feasibly, realistically, to combat any kind of climate change?
Again, I think that's probably a question for the end, right? We're hoping to get through the day.
We're running out of time.
There's an after session, isn't there?
Yeah, there is an after session. We don't have to leave here.
We might not all.
Yeah, I know I have to go to the end.
So getting back to the plant thing, plants do like CO2, so it's good for them, but there's been a lot of studies on this. There's actually some other influences. So plants can only uptake increased CO2 if they have the water resources they need, if they have the other trace nutrients and stuff. But generally, yes, plants like CO2.
Well, in fact, doesn't the higher CO2 concentration help plants do with less water? I mean, plants have difficulty keeping water in and letting CO2 get in, right? I mean, water tends to
There's
get
like
out
a
the same.
sweet spot where when they get enough water and extra CO2, then they love it. But then, it's easy to, water actually is a huge issue, yes.
I don't understand the process, but I thought there was a certain percentage where too much CO2 is bad for the plant. You can't, something happens with the growth is just.
At least I've not heard that. In fact, many greenhouses, they bring the CO2 level up to 1,000 parts per million or more, I believe. In a greenhouse, you have the ability to do that, and that is done.
And the other comment I had was, what about the ocean when you have CO2?
He's getting to that.
That's this slide.
Yep.
So a lot of people like to talk about ocean acidification, which kind of bothers me because it's neutralization as far as I'm concerned. Because you don't become acid until the pH is less than 7. But that's kind of the writer's favorite, I guess. But anyway, this is again an IPCC chart which shows historical data and some projections depending on how much fossil fuel we burn in the future. And a lot of people think this is extremely worrying. And I mean, maybe it could be, but at least the next piece of data I think is interesting shows that the modern ocean pH is probably higher, it is less acid, than almost all of the preceding 270 million years. Right? That, the graph here at the bottom, just a little bit.
Can we go one more?
Yep. That this is pH versus time. This now we're going backwards in time, so this is modern times going backwards. And the pH 100 million years ago was only 7.6 approximately, at least if you believe this data. There's questions always about data. But, at least it says that the oceans did not die when the pH went down in the 7th.
Well, see, again, it's unfair. Some creatures did die.
Well, sure they did, but the oceans didn't. Right?
Yeah. What does that even mean? Yes, not everything died.
Well,
it was always, everything that changes is good for some creatures and bad for others.
Absolutely. I'm just saying, that it's not distinguished. It's not making all life on the planet extinct to have the.
There is no question about that. Yeah.
Okay. Because I mean, there's a lot of science fiction that has that happening. So,
yeah. Okay. It seems unlikely, actually, that we're going to kill off all life this way. We'll kill ourselves off, but it's not clear we'll kill all life.
We'll grow gills.
So how are we going to kill ourselves?
Well, basically, Homo sapiens came out of the last glacial period, right? 60,000 years ago. Oh, I'm sorry. Okay, so modern humans basically evolved over the last couple of glacial periods. We're essentially cold adapted. We have a high body temperature, and it doesn't need to get very much higher before we don't function. The clearest example is people that die in hot tubs. You get your core body temperature up to 140 degrees and you're toast. And so basically there are places on Earth now that are close to that happening. And it's a combination of temperature and humidity. If you have high humidity and high temperature together, you can't, sweating doesn't help you, so you can't cool yourself, so you can't actually survive outside. So that's basically what's going to kill humans off as the temperature gets high enough.
That's it.
So, but that doesn't mean all life on Earth. Some of the life on Earth is going to do great. It's going to love it. Lizards, snakes, crocodiles are going to do really good.
Okay, so we had a request for comparison with models, and Robert hasn't had a chance to talk very much, so we're going to go to his slide. His first slide is a comparison with models.
What you're seeing here are some 90 models and their predictions. The correct time frame is right about here, isn't it?
That's where the black line is.
Yeah.
Yeah, right here. This is our current time, and these are these models pushing into the future. Here they are applying the appropriate parameters and what they predicted. Now, this line that you see here is the actual data. This is what temperatures actually were, and I think the comment here is pretty interesting. Over 95% of the climate models agree, so maybe the observations are wrong. My whole point in showing this is very simply that this is not settled science. This is open to interpretation, and it's open to new ways of looking at it, and even new reasons why things are happening. And if we can just go through we don't have to look at every one of the slides, but I'd like to get to the solar portion if we can.
Tell us which one to go to.
Okay, just start.
That's the one we saw.
Yeah, so just move a little further, or just stop for back one.
Back.
Yeah. Keep going.
So we had a comment from the audience that everyone believes climate change is happening and that it's humans are responsible. And when we're preparing for the panel, I have to say we're not totally in agreement on the panel.
Yeah. And I'm not trying to be controversial here. I'm just trying to say that there are other ways of looking at the data. And it's kind of interesting here when you look going back from 1400 and on up to the present. You're looking at sea level changes. And you notice that there's a periodicity to sea level changes. Okay. Well, let's go on to the next slide. Next one. That one. Okay, what you're looking at here now is solar irradiance, the amount of energy that's arriving at the Earth from the sun over periods of time. And you'll see that there is something that's known as the Maunder minimum between 1600 and 1745 roughly. You've got the Dalton minimum here. You've got some other minimums, and we're current. And you see the variability of the sun. And this is hard data, just like the other data we've been looking at is hard data. The amount of carbon dioxide in our atmosphere, that's hard data, that's real stuff. And what we have to ask ourselves as people, as researchers, even though we have a feeling for this is how we think it's happening, there's very good reason to think that maybe the sun, rather than human activity, is driving this, and maybe solar output and what the Earth is receiving from the sun is what's giving us the climate changes. And you notice what's happening here. We're headed downwards, and the people who are looking at this particular model are saying that we're headed now into a mini ice age, and that by the roughly 2030, our temperatures are going to be down where they were in the modern minimum, or perhaps the Dalton minimum. It's going to be dramatically different from what we thought it might be based upon the carbon dioxide driven models. I'm not propounding one or the other. I'm simply saying there's a lot of question there. And one final comment, the mechanism by which the sun causes this to happen has been fairly closely looked at, lab experimentation and actual physical measurements. As the sun has more activity, it puts out more charged particles, which are captured by the Earth's magnetic field, and this forms a shield for cosmic radiation coming in. And lab experiments over the last 7 or 8 years, and if you want more data, I can give it to you, have shown that 30% of Earth's cloud formation are caused by influx of cosmic radiation. So the more cosmic radiation you have coming in, the more cloud formation you have, and the less cosmic radiation you have coming in, the less cloud formation you have. So you got a lot of solar activity. You have you block all of the a great amount of the cosmic rays, and you end up with a less cloudy and warming Earth. And when you have a quieting sun, you no longer have the protective layer, if you will, of charged particles, and you end up with many more solar radiation, cosmic radiation coming in, much greater cloud formation, and the end result is cooling. So you have a mechanism that is a real mechanism that can explain everything that we're seeing that is entirely different from the carbon dioxide driven model.
Well, the thing is, while you've got that going on, while you've got the amount of solar input changing, the cloud cover changing, meanwhile, we have created this higher CO2 level that has been present for a rather long time. So
We don't know that the carbon dioxide is driving the warming process. That's an assumption that's built into the models, and you saw in the first slide how well the models match reality.
I was talking about the greenhouse effect is something that can be empirically measured. The transmission of the atmosphere at different wavelengths.
Yeah, well, that's a good point. Maybe I can summarize it real quickly for everyone. Is that there's some pretty solid thermal radiation physics that say if you double the carbon dioxide and everything else stays the same, cloudiness stays the same, absolute or specific humidity stays the same, that the temperature should go up about 1.1 degrees Celsius from doubling, which is a lot less than the models say, right? The models say, well, because of all these things that do change, the temperature should go up 2 to 4 or 5 degrees. So there's a huge difference, and I think the models can be completely wrong. There could, in fact, be feedback effects that are not positive but negative to make it less as well. Well, it seems somewhat unlikely. Yes, the question.
Actually, the lady here has a question.
Oh, yeah.
It was very close to what he had asked. We didn't have all the people that we do now back when we had some of these other numbers. And the carbon dioxide that people emit, it was very close to what his question. Where is it going? Isn't that going to count for some of our warming? And he asked that question about the carbon dioxide and the greenhouse effect.
I didn't totally understand the question here.
Was there another comment over here?
No, that was.
I want to say the sun is super important. I totally agree with that. I do think that scientists have a good handle, though, on the relative contributions of the sun versus the carbon dioxide in the atmosphere. There have been a lot of studies on that. And I agree that based on the sun stuff, it looks like we might have, from the sun, the cooling coming up. So I guess we'll see in the future, is it going to be cooling or not?
We will definitely know that.
I might also point out the numbers, there are numbers here on exactly what it is, and they're pretty small changes in solar irradiance, right? So there are reasons why people might say that this isn't controlling, but, it should all be considered.
Can I ask?
Comment over here.
I'm just wondering how they can measure that solar irradiance in the 1600s.
It's done from ocean cores, from tree rings. There are a whole bunch of various projects.
I guess we're done.
We're supposed to have this extended time in here.
Oh,
It's the other room? Okay, well, I guess we're done.
So thank you, everyone.
did you enjoy that footage? I know it ends abruptly, and I told you about that before you started up there, but I want to know what you thought of it. Let's argue this out in the comments. Tell me what you thought of the climate change hard data panel. I love the things that it brings up. You see, I'm one of those people who I love documentaries. I buy quite a bit. Here's some of the ones that I have on climate change and such. And you know what? I've seen all of them. I've seen them all. I've read through all their stuff. I spend a lot of time watching and learning. I do, and well, I hope you do too. Let me know what you think of this in the comments below. Hit that thumbs up if you haven't already. Hit that subscribe button if you haven't already. Hit that share button if you haven't already. Remember, subscribe, like, share, and then hit that little bell so that you know whenever we have brand new episodes, or rather brand new videos here on Area DMG. And until the next video comes out, you are now caught up.
You realize, no, it's not really about making the most money. It's about achieving your artistic vision.